Now, unlike common perception, analog circuit analysis and design is black magic. It is not. It is not. It just takes a lot of experience. It takes a lot of analytical skills, a bit of your creativity, a lot of your creativity actually. And then, yes, you will be able to design a complete IC, a successful IC, if you are thorough enough with your concepts. It all boils down to your understanding of how the transistor works. And that is the most basic thing. Once you know that, everything is easy. Everything is very easy. And knowing that is also very easy, actually. So because one more thing that I want to share, I don't, which I feel it is important. There's a course called semiconductor physics. There will be something by that introduced to the physics behind a transistor. It's a course which actually gives you very good knowledge about what is there in a transistor, and when you know that, you feel confident that okay, I'm doing something which I know about till the very physics of it. And when you know that, there is a different confidence in you in proceeding forward. And if you take that mindset that you want to understand each and everything which is involved in it, it can be overwhelming, but it is fruitful, and it will turn out to your advantage only. Basically, there are two. Now, let's come back to this analysis versus design part. I think I have told you a lot of it in the previous slide itself, but I'll go through it again. So, circuit analysis is nothing but you have a circuit, you try to break it into small parts. You try to understand it. So, anything when we try to any big problem, when we try to understand the best part is we divide that problem into sub problems and then try to solve them individually. And that helps in the understanding world also. When you want to understand something big, you break it into pieces and you try to see and you try to understand the basic pieces behind it. Let's say there is one amplifier, right? There is one diff pair, a differential pair. There is some part of the circuitry which is providing the bias current. So all those things, when you break it, then it will be very easy for you. You will be looking at a circuit and you will be telling it, okay, this is what it is doing. I'll try to bring in some circuits in the slides as well, where all we will do is nothing but just look at the circuit and try to understand what it is doing. It's a very interesting way to actually learn what's happening, and whether we are actually aware of, okay, whatever we have learned is actually making sense to us, and we are able to make sense out of that information. So that will be one way which will be used to give you a very basically from the analysis point of view, the understanding of the circuits. The circuit design now is nothing but when you evaluate your circuit. Now, let's say you want to design a current, something which provides current to your very basic current to your amplifier. Without current, it cannot work, right? You need to have a DC operating point first of all, on top of which, if you give some analog signal, it will work as an amplifier. Now, okay, since I have brought that word DC operating point, if you choose it correctly, your transistor will work as an amplifier, or if you choose it very low or very high, it will act as a linear device, basically just as a switch. That is what your digital circuits are actually, just breaking it. So this is what analysis and design is. I hope this is clear to you guys. And the design skills are actually, this is very important. These are required by learning by doing, and it is very important for you as an analog design engineer to, whatever idea that you have, whatever problem that you think you have solved, you first evaluate it, get your equations ready, and then simulate it to see, okay, if it is actually working. And while doing that, you will learn a lot of things which are required, which are important for the process of delivering a very robust IC. There will be a lot of things, a lot of unexpected things that will be there, and you will realize that once you go through that process. And that is why we'll have a design project for this course. Apart from every week, the circuit I'll be sharing with you, that is not a project. That is just a circuit to share your thoughts on. I'll be listening to your thoughts. What do you think about it? The design project will be completely different. It is going to be a challenging task. Now, the intent of this, what is the intent of this course? Now, as I have told multiple times, this is a field which is very interesting, very intriguing because of the challenges involved in it. But it takes several years of experience to master because of the hidden variables that we can't see right now, that you can't see right now, because it's not taught in the colleges. It's something which industry specific, and we learn that every day when we are designing circuits. Now companies also prefer engineers who have enough who have enough experience designing circuits. The reason being that I've told you, no one likes their chip to be dead in the end, and no one likes to blame anyone. And good companies don't do that. They just try to see, okay, what was the fault, and no one wants to be in that loop. No analog designer, no engineer wants to be in that loop when something goes wrong. There's someone, okay, this is the reason it went wrong. So it requires experience, and we make mistakes. Mistakes are necessary, they are important, and that's how we have moved to this point where we can actually evaluate on based of the previous mistakes people have made, and you will be making new mistakes. That is totally fine. You don't need to be afraid from that. But all you need to do is whatever is there, you don't get the basic thing wrong. That is very important, and that I'll be trying my best to teach you that. Sometimes I do that as well. A lot of everyone does that, but it's our job to actually try not to have our basics wrong, and that is actually the most important thing about analog design. Clear basics, basics about gain, bandwidth, basics about how the transistor is working, basics what industry demands and what is taught in college, and this course will be specifically bridging that gap. And but please note that whatever you learn in college is equally important. As I have mentioned, electromagnetism is a course that you should not take it. It's a difficult course to grasp, but give your time. You will get hold of it. Give a little time. And semiconductors physics is one. If possible, take RFIC design as well, because all these things, even if you are not very proficient in it, it will give you a very good idea about what this field holds, and that is important because learning will happen all your life. But the very basic thing that you will want to have is that the idea what this has to offer, and what will be your job when you will be actually pursuing this. So the opportunities that you will have after analog or RF design. RF I won't be covering because it's a vast sea. It's a different subject altogether. But I'll be going for the low frequency part of the analog design. So okay, I'll make that clear. When we talk about analog design, it starts from very low frequencies to very high frequencies till optoelectronics. So sub gigahertz, then your mobile phones, your reception, then above 1 gigahertz are your Wi-Fi, Bluetooth signals. That is also analog RF. Then you go to microwave. Then millimeter wave comes into the picture where your radars are actually working. So all this is one electromagnetic spectra. That's why I say that you need to understand this electromagnetism, because even if you're not designing an analog circuit, if you have a good enough understanding of what is there in the full spectra, there will be nothing stopping you from being successful in this field, or any field for that matter involving semiconductors. So the research opportunities, as I've already discussed, that interface that we have between analog and digital world are the data converters, analog to digital converter or digital to analog converter. It's a very wide, actually very important research topic, because today what we want is that as soon as we get a signal, we give it to the ADC, and it's actually not possible. It's today. I mean, it is possible if we can actually build basically a very low LSB data converter, and generally noise is what precedes the signal that we get. That's why we have an amplifier, before this ADC. So it's a research topic which is very widely taken by students. There is very low jitter frequency synthesizers. Now, what are frequency synthesizers? Now you know what a clock signal is. So you might have heard about this in your Intel processor or your AMD processor. That okay, this is a 2 gigahertz clock, or 3.2 gigahertz processor. That is a clock speed basically, and that to generate that clock, there's a circuit which is called a phase lock loop. So you don't want your clock
to basically be, when about a rising edge of that clock or the falling edge, it should come at the same intervals always. Any change in in the rising edges, any change in the time of it is noise, is jitter basically, and we want to minimize that as much as possible, as much the accuracy, according to the accuracy we want. So that is what frequency synthesizers are. Then, as I've told you, analog processor. It was there in 80s, 1990s, but then this was dropped because of the introduction of digital processors. Now we are going back to them again, and because the AI/ML requires that, because of the processing capabilities and the battery efficiency that it gives. Then there is something called automated analog design, where today we have tools to just PNR tools to make a digital circuit, where we write an RTL code and the digital circuit is ready. But analog design, as you have seen, the knobs that are there, all the variables that come into picture, it's a very, very difficult task to automate a circuit. Okay, you want to design this op amp, this bandwidth, this frequency, and a tool giving you that, it's actually very, very difficult. And research is going into this, people are working into this, but it's a very far-fetched thing right now. But yes, it's a very topic which receives a lot of interest from people all over the globe. Okay, then there are RF circuits like power amplifiers. Power amplifiers is also a very hot topic. When your Wi-Fi router, for say, or yeah, let's talk about Wi-Fi routers first. So there is a power amplifier before that antenna which is giving you the signal. Now that power amplifier has to give good enough power so that you receive that power. Also, of course, there is a limit on how much power you can send. Why? Because you cannot disturb other bands in which are there. You cannot disturb other frequency bands, and that's why there is a regulatory body which takes care of that. That this is the maximum amount of power that you can give, and in other bands, in other frequencies, that power cannot leak, and that is why you need high linearity also. So you might not be getting completely what I'm trying to say with this right now, but just make sure that when RF comes into your curriculum, pay good attention to it. It's a very interesting field, and it takes a lot of an analysis and a lot of focus to get it right and to understand it. And once you know this, your world is a lot easier. It will be very easy. You will be never short of opportunities. Research is again going on a lot. So I have actually, if someone wants to go for some university, you can contact me. I can guide you what curriculum is good at what you need, because I have done it myself. I have done a lot of that research, and so wireless power transfer is my personal where I actually want to do my work. And then there are self-powered nodes everywhere. You see today IoT, 5G, all those terminologies you see. It's nothing but a connected world, and that connected world means connected sensors. Where sensor nodes, and you cannot just change batteries. If you just imagine, you have a lot of sensors. You have a smart home. Everything is they have a lot of sensors in your home to make it smart, and you just can't keep on changing those batteries, or you have just give a supply to them. It will be difficult. Now just imagine they are charging on their own because you have so much of let's say RF energy. Your Wi-Fi is splitting out energy everywhere. Then like if you can use all that energy and charge yourself and sustain, right, it's a very good problem solved basically, and that is very well appreciated. So we have RF energy harvesters as well. I have worked in this domain as well. So if any of you are interested, you can contact me. I'll try to guide you as to the best of my knowledge. Then there are ultra small, ultra low power circuits for biomedical applications. So there is this team in MIT which is working on actually whatever neurons in your brain is doing. They are actually trying to do that with very small circuits. Try to pass that information from one neuron to the other, and that can actually alter your wiring in the brain, and it can actually control your so it's a very long shot, I mean, but yeah, people are working on that to make your memory to have it configurable. The research is going in that. Looks like a sci-fi thing, but every sci-fi thing which was there in 1980s, 1970s is true now. So yeah, so after 40, 50 years or whatever, I mean, I don't know when they'll be able to do that. They have actually made a lot of progress there. So people are working on that as well. It's a very hot research area as well. Now, the job opportunities that you have, it's a specialized field, as I have mentioned several times, and there are a lot of opportunities and positions which often goes, unfilled due to lack of good engineers. And with this upcoming boom of industrial revolution 4.0, IoT, 5G, AI, all those fancy terms that we hear, one thing that you have to take from it is that the analog design engineers demand will be at an all-time high, because all of it requires circuitry. All of it is about, this is actually a semiconductor industry driven thing. No one will tell you this, but more the number of chips, more the profit will be there will be in the industry. And it's not about just the number of chips, it's about how you can make your life easier and how we can be at the peak of our efficiency. And this is what semiconductor industry has been doing all this while, and has been very successful in it, and I'm proud to be a part of it. So as I have told you, the third point is analog design is very difficult to automate because of the area variables involved in it. But yes, as I have told you, it's an active area of research. And analog processors also, right, for AI, it's a very hot topic. I mean, all of you who have that thing in mind that they want to go for research in future for masters, these are some topics which you should definitely give it a thought. And needless to say, if you know your subject, you will never be short of offers. If you know your subject well, you have your basics. It's very just the basics. Just the basics are clear. You will build anything on top of it, and you will be successful. I hope to see you soon.